Okay, we've got a big and interesting goal for this video, and that is to classify all the real numbers between 0 and 1, where this dilogarithm function, in other words, the sum as n goes from 1 to infinity of x to the n over n squared is nice. And what I mean by nice is you've got some closed form in terms of elementary functions. And so we're going to use the following tools. So what I don't have written on the board is we're going to have an integral formula for this dilogarithm, in other words, for this sum. So we're going to derive that first. And then also we're going to set this function L of x equal to this Li2 of x, this dilogarithm function, plus 1/2 natural log of x times natural log of 1 minus x. That's going to be an important function to work with. It'll simplify some of the calculations. And then we're going to prove this following lemma, which has two parts. And that is L of x plus L of 1 minus x is pi squared over 6. And also L of x equals L of x over 1 plus x plus 1/2 L of x squared. And we'll get all of these nice values out of this lemma. Okay, so the first thing we want to do is find a closed integral formula for this dilogarithm, this Li2 of x. So let's look at what we need to do. So we'll write Li2 of x, so that's going to be the sum n equals 1 to infinity of x to the n over n squared. Okay, so from here what I want to do is take out a 1 over n. So I'm going to write that as the sum n equals 1 to infinity of 1 over n times x to the n over n. Okay? But now we can notice that that is just the antiderivative of something. So we can take this term and rewrite it in the following way. We'll write this as the sum n equals 1 to infinity of 1 over n times the integral or the antiderivative from 0 to x of t to the n minus 1 dt. So we've replaced that thing in that box by that antiderivative. Okay, so now we're going to essentially do the same thing again, but we're going to reverse the order of the sum and the integral a bit. So we can bring the integral out of the whole thing. So we're actually using a theorem here that allows us to interchange the sum and the integral, which I won't state, but you can look it up if you're psyched on that kind of thing. And now we have inside of that is the sum of 1 over n, and this is n equals 1 to infinity, times the t to the n minus 1 dt. Okay, good. Now, notice we kind of want this 1 over n to match the exponent of t, so we can do this trick again. And so how we can get that is by factoring a t out of this sum. And so that's going to give us the integral from 0 to x of 1 over t times the sum n equals 1 to infinity of t to the n over n, and then we have dt. So now I'll put that sum in parentheses. And we can do the same thing again. Notice that sum in parentheses can be written as another integral. So here we have, this is equal to the integral from 0 to x of 1 by t. And then that thing can be written as the sum n equals 1 to infinity of the integral from 0 to t of u to the n minus 1. And now we have du dt. So let's see, we just rewrote that part in the following way. But the great thing here is that now this thing is just a geometric series, so it's easy to see that this bit right here, we can bring the sum inside the integral, and we'll get that this is 1 over 1 minus u, because it's a nice geometric series. And so that gives us the integral from 0 to x of 1 over t, the integral from 0 to t of 1 over 1 minus u du dt. Okay, great. But now we can take the antiderivative of this stuff that's inside of the t integral, in other words, the u integral. And what we'll see is we get a natural log there, but we have to tweak it with a minus sign because of the chain rule. So what we end up with is this is minus the integral from 0 to x of the natural log of 1 minus t over t dt. So that's what we get for this dilogarithm function in its integral form. It is, so let's maybe summarize it over here. This dilogarithm function is equal to minus the integral from 0 to t of the natural log of 1 minus t over t dt. And this is the formula that we'll be using for the dilogarithm function from now on instead of this sum formula, because it makes the calculations a little bit easier. Okay, so I'm going to clean up the board, and then well, we're going to define this function L of x as follows, and then we're going to prove this lemma. Okay, so now we're ready to look at the proof of the first part of this lemma. So we want to look at L of x plus L of 1 minus x. Okay, but then substituting in for this L function, notice that's going to give us this dilogarithm evaluated at x minus this dilogarithm evaluated at 1 minus x, and then we'll have plus 1/2 the natural log of x times the natural log of 1 minus x, and then minus 1/2 the natural log of 1 minus x times the natural log of x. Okay, great. So just so that we're keeping score, this and this make up our function L of x, and then this term and this term make up our function L of 1 minus x, and I just realized here I need plus signs instead of minus signs, so we're good. Okay, great. But now we can replace these dilogarithms with their integral form. So this one in yellow is going to be minus the integral from 0 to x of natural log of 1 minus t over t dt. Okay, good. And then this one in red is going to be minus the integral from 0 to 1 minus x of natural log of 1 minus t over t dt. And then those two natural log type terms combine to give us the natural log of x times the natural log of 1 minus x. No longer is there a half there. Okay, great. So now from here what I want to do is go up to the beginning and set this equal to some function f of x. And then I want to look at the derivative of f of x. So we can calculate this derivative using derivative rules over here and using the second fundamental theorem of calculus for these integral terms. So using the second fundamental theorem of calculus, notice this one is set up perfectly. So we just plug this x in everywhere we see t. So that's going to give us minus natural log of 1 minus x over x. So that is the derivative of this first term. Okay, and then now we're going to have minus, so here we plug 1 minus x in everywhere we see t, but then we have to include the derivative of 1 minus x because of the chain rule. That's going to turn this minus sign to a plus sign because the derivative of 1 minus x is -1, and then we get the natural log of x over 1 minus x, because if we plug 1 minus x into 1 minus t, we're going to get x. Okay, and that is going to be the derivative of this second integral. Okay, solid. Now we can take the derivative of this using the product rule. So taking the derivative of the first part, we get the natural log of 1 plus x over x. And then the derivative of the second part, we get the natural log of x over 1 minus x. But we have to, again, include a minus sign because of the chain rule. But notice what happens here is that this term cancels with this term, and this term cancels with this term, so we get that this is equal to 0. So this f prime of x is always equal to 0, but what that tells us is that f of x is equal to some sort of constant. So now we just have to pick some value that we can plug into f of x where we know what that constant is, and maybe we'll plug in 1. And you might say that's problematic because over here you see that you would get a natural log of 0, but you can take care of that by taking limits. And so I won't do that. I'll just plug in 1. So notice if you plug 1 into this, you're going to get Li2 evaluated at 1 plus Li2 evaluated at 0 plus this natural log stuff. Plus this natural log stuff, but notice that is just going to give us 0 by taking the appropriate limit. Okay? And then also, notice if you plug x equals 0 into this, you're going to clearly get 0 because that's just the sum of all 0 terms. So what we're going to have here is the dilogarithm evaluated at 1, which is the sum n equals 1 to infinity of 1 over n squared, which is a well-known Euler sum, which is pi squared over 6. Okay, so let's see what we've got here. We have f of x equals a constant, and then we found that one value of f of x equals pi squared over 6, but since f of x equals a constant, that is all values of f of x. But then f of x was this combination of the two L functions, which gives us this formula right here. Okay, so we've proved this lemma, and now we're ready to move on to the second part. Okay, so now we're moving on to this next part of the lemma where we want to prove this formula. And so we're going to approach it a similar way. So let's consider a function g of x, which is the right-hand side of this minus the left-hand side of it. In other words, it is L of x over x plus 1 plus 1/2 L of x squared minus L of x. Okay, so let's write that out in terms of the dilogarithm and its integral formulation. So notice this is going to be minus the integral from 0 to x over x plus 1 of natural log of 1 minus t over t dt plus 1/2 natural log of x over x plus 1 natural log of 1 minus x over x plus 1, which is going to be 1 over x plus 1. Okay, so just to reiterate, that is this part right here is given by all of that. Okay, good. Now we're going to have this is plus 1/2 times that L of x squared. So we're going to replace that in this way. Okay, so that's going to give us negative the integral from 0 to x squared of natural log of 1 minus t over t dt plus 1/2 natural log of x squared times natural log of 1 minus x squared. Okay, good. And what we have just written down is this second part. And then finally, we're going to subtract from that minus the integral from 0 to x of natural log of 1 minus t over t dt plus 1/2 natural log of x natural log of 1 minus x. So now what we can do is simplify this using logarithm rules and stuff like that. So let's see what we get. This gives us g of x equals, so let's maybe put all the integral type terms first. So this is going to be the integral from 0 to x over x plus 1 of natural log of 1 minus t by t dt. So that's this first integral type term. And then we have minus half this second integral type term, which is the integral from 0 to x squared of natural log of 1 minus t over t dt. Okay, great. And then finally, this is going to be plus the integral from 0 to x of natural log of 1 minus t over t dt. Okay, so that's what we get for the integral type terms. Now let's see what we get for the log type terms. So here I want to use logarithm rules to simplify these things. So notice I can take this one and I can write it as 1/2 times the quantity. Here I have natural log of x minus natural log of x plus 1. So I know that because I've got a quotient inside my logarithm. And then this, since the x plus 1 is in the denominator, that's going to turn it into a minus, which I can just factor out of the whole thing. And so I factor that out of the whole thing, and I get the natural log of x plus 1 like that. Okay, so that's what I have for that first term, and then I can do something similar for this second term. Notice I can bring this x squared, the squared out front, and that's going to cancel this. And then I can rewrite 1 minus x squared as 1 minus x times 1 plus x. And that's going to give me plus natural log of x times natural log of 1 minus x plus natural log of 1 plus x. Good. And then finally I have this last term, which is plus half natural log of x, natural log of 1 minus x. Okay, so that's my function g of x. So I'll take that function, I'll move it to the top, and then we'll get on to the next step. Okay, so I've moved the function g up to the top of the board, and I've done some simplification with the natural log stuff just by distributing and combining like terms. So there's not really much to that. So now I want to do the same kind of thing that I did on the last board, which is look at the derivative. So I'm going to look at the derivative of g, and I'm going to look at the derivative of g taking these with the fundamental theorem of calculus part 2, and then just using differentiation rules on this type term. So for this first term, what we need is we're going to have minus the natural log of 1 minus t, where t is evaluated at this thing right here. So notice that's going to give us 1 over 1 plus x. That's what we get, over 1 plus x. So that's what we get for that first one. And then we have to multiply that by the derivative of x over x plus 1. We use the quotient rule for that. So notice that's going to be x plus 1 minus x over x plus 1 squared. So we get something like that. Okay, so that is the derivative of this first term. Okay, great. Now let's take the derivative of this second term. So notice we're going to plug x squared everywhere we see t and remove the integral, and then we have to multiply by the derivative of x squared, but that's nice, that's just 2x. So that's going to cancel this, and we're going to get minus x times the natural log of 1 minus x squared all over x squared. And then I have a 2 in the denominator still. Okay, good. And then maybe plus dot 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 for the plus of the rest of them. Okay, good. And then now I can take the derivative of these next terms using the product rule. So notice the derivative of this first one is going to be 1/2 natural log of 1 plus x over x plus natural log of x over 1 plus x. So we get something like that. And then the derivative of the second one is going to be similar. So I'll let you check all the details. They're pretty elementary, but what you'll end up with is that everything will cancel, and you'll get the derivative of this is 0. But now if g prime of x equals 0, that tells us that g of x is some sort of constant for all values of x. But the next thing that we can easily check is that if we plug 0 into this, we get 0. Which tells us that that constant equals 0. So in other words, g of x equals 0 for all x between 0 and 1, because that's the interval that we're interested in, which tells us that L of x equals this combination of these other values of L. In other words, we've proven the second part of the lemma. Okay, so now I'll clean up the board and we'll get to the next part. Okay, so now we're going to look at some values of L of x. So as we've already seen, L of 1 is equal to pi squared over 6. Okay? And then notice that if we plug 1/2 into this equation, we get L of 1/2 plus L of 1/2 equals pi squared over 6, which that tells us that L of 1/2 equals pi squared over 12. Because notice plugging 1/2 into there, we have two of the same objects. Okay, good. So now the next thing I want to do is let's set x1 equal to 1/2 times -1 plus the square root of 5. And let's set x2 equal to 1/2 3 times negative the square root of 5. And so I do that because those are going to work well when plugged into this next functional identity for for this function L of x. Okay, so now with these two numbers, we have some nice identities satisfied by them. For instance, we have 1 over x1 plus 1 equals x1. Okay, good. We have 1 minus x1 equals x2. And then finally, we have x1 squared also equals x2. Okay, so we can use the fact that these numbers satisfy these rules along with these two equations that we proved in order to find values of L of x at this x1 and x2. So let's see how that goes. So notice L of x1 plus L of 1 minus x1. So that's going to be the same thing as pi squared over 6 on the one hand because of this formula. But then on the other hand, we know 1 minus x1 is x2. So that gives us L of x1 plus L of x2. Okay, good. So now let's hold on to that equation and then move on to using this second identity. So notice we also have L of x1 equals L of x1 over 1 plus x1 plus 1/2 L of x1 squared, and that's from that second identity. But notice what we have here is 1 plus x1 in the denominator is the same as x1 in the numerator, so that gives us x1 squared here. So in other words, here we have, this is 3/2 L of x1 squared. We get 1/2 from this term and then 1/2 from this term, again, just by multiplying this equation by x1 in the numerator. But notice x1 squared is equal to x2, so that gives us, this is 3/2 L of x2. Okay, so now let's look at the extreme left and right hand side of this. And notice that the red boxed equation and the yellow boxed equation allows us to nicely solve for these values of L. So we have L of x1 is given by pi squared over 10. So that's easy to check just by mashing those things together. And then L of x2 is equal to pi squared over 15. Okay, good. So I'm going to clean up the board. I'm going to move that information up, and then we're finally ready to apply that to our nice sum. Okay, so let's look at a quick summary of all of the tools that we have developed. So we've found that our dilogarithm, in other words, the sum as n goes from 1 to infinity of x to the n over n squared, and this is for x on the interval 0 to 1. You can actually extend this a bit, but we're not going to worry about that. You have to worry about complex values of the logarithm. So this equals our function L of x minus 1/2 natural log of x, natural log of 1 plus x. And then we found these 4 nice values of this function L of x, and we're not going to prove this, but on the interval 0 to 1, these are the only nice closed values for this function L of x. So we've got L of 1 is pi squared over 6, so that's just Euler's famous sum. L of 1/2 is equal to pi squared over 12. L of 1/2 times the quantity -1 plus root 5 is pi squared over 10, and L of 1/2 3 minus root 5 is pi squared over 15. So now we can use those values of L to find some nice values for this sum. So I won't write down the one where x equals 1 because that's one that's well known that we've already written up. But from all of this work, we get the following types of stuff for free. So if we plug in x equals 1/2, we get 1 over 2 to the n x to the n. So that's going to be equal to L of 1/2, which is pi squared over 12 minus 1/2. And then you get natural log of 1/2. And then, I apologize, this should be 1 minus x there. You get natural log of a 1/2 again. So this is the natural log of 1/2 squared. So that's what we get for that. So now let's look at these others. So here we get the sum n equals 1 to infinity of minus 1 plus root 5 to the n over 2 to the n squared. Sorry, this should have been n squared up here. Okay, cool. So that's plugging in x equals 1/2 times -1 plus root 5. So that's going to give us pi squared over 10 minus 1/2 the natural log of 1/2 times -1 plus root 5 times the natural log of, so if you do 1 minus that, you're actually going to get this next term, 1/2 3 minus root 5. Good. So we'll get that. And there's actually a way to simplify those natural logs, but again, I'll let you guys think about that. So now let's look at the last one that we know. So this is the sum n equals 1 to infinity of 3 minus root 5 over n, 2 to the n squared. So this is going to be equal to pi squared over 15. Okay, which we get from that first bit, and then minus 1/2 the natural log of 1/2 3 minus root 5, and then times the natural log of 1 minus that, but then again, I'll let you check that 1 minus that brings you back to this guy, so that's going to be 1/2 -1 plus root 5. And again, you can do some simplification on those terms as well. Okay, so again, this is all like the nice closed elementary forms for values of x plugged into this sum on that interval. It's a good place to end this video.